We were talking about amounts in chemical reactions and how to calculate how much of a product could be made, things like that. So let's go back to our pizza example. And our simplified pizza recipe was 1 crust, 5 ounces of tomato sauce, 2 cups of cheese, and 1 pizza. So if we have 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce, how many pizzas can we make? Can you answer that just bang real quick? 3 and 4. How do you go about thinking about that? Well, 4 crusts would make how many pizzas? 4. And you can do that in your head, but 4 crusts, yeah, my stylus apparently is tired too. 4 crusts times 1 pizza per 1 crust gives us 4 pizzas. And how many pizzas could we make from 10 cups of cheese? 5. But if we only have 4 crusts, could we really make 5 pizzas? No, we couldn't, because we'd run out of cheese. And what good is a pizza without cheese? That's not really a pizza. Pardon me? Oh, I'm sorry, yes. Brain dead. We run out of crust before we run out of cheese. Backwards. Yeah, you really can't have a pizza without a crust. Then you've just got cheese on a plate. So 15 ounces of sauce. How many pizzas? 3. Because it takes 5 ounces of sauce. And so 15 divided by 5 is 3 pizzas. And so in this example where we can think about the ingredients, because we're familiar with things like this, we recognize that when we've made 3 pizzas, we have run out of sauce, and the pizza making stops, right? So here it is in pictures, just in case your visualization part of your brain was dead today. So we can only make 3 pizzas. And the sauce is what's limiting how much pizza we can make. And so thinking of the ingredients as reactants, we would say that this sauce is the limiting reactant because it limits how much product can be made. And the approach here is that we're taking each of the ingredients and calculating how much product we can make. And it's the smaller amount, the least amount of product that becomes the amount that can be made. Because when you make that amount, you run out of an ingredient, and once you run out of ingredients, production stops. So we say that the tomato sauce is the limiting reactant, sometimes called the limiting reagent. It's the reactant that makes the least amount of product. And that's the same terminology we use for chemical reactions. The number of pizzas that we calculated there, 3 pizzas, that's called the theoretical yield. Because that's if everything goes perfectly, we could make 3 pizzas, right? But what if on the way to the oven you drop one? Well, you can't serve pizza that you dropped on the floor. So the theoretical yield is the amount of product that can be made in a chemical reaction based on the amount of limiting reactant. Okay, so the limiting reactant is what controls the amount of the theoretical yield. Well, just like in cooking, where you rarely have exactly the right amount of ingredients to make your desired thing, like if you're making pizza, it's really unusual to have just the right amount of crust and just the right amount of sauce and just the right amount of cheese. Usually one thing is going to limit what you make. The same thing happens in chemical reactions. We rarely have just the right amount of each chemical in a reaction. And so generally one reactant will be used up before the others. When the reactant gets used up, the reaction stops. And that reactant limits the reaction, and so it's called the limiting reactant. The ones that are not used up are called the excess reactants. So in our pizza example, what were the excess reactants? The cheese and the crusts, right? We had some of those things left over. So the amount that's actually made is called the actual yield. Isn't that cryptic? The actual amount is the actual yield. If you burn one or drop it on the floor, then we really end up with only 2 pizzas that we could serve, right? So even though in theory we should have been able to make 3, we screwed up and we only ended up with 2. That's the actual yield. And we use percent yield as a way to express how efficient we were in making pizzas or in a chemical reaction. And let's see, is this on the next slide? No, it isn't. So the percent yield, I will give you the equation here. The percent yield, it follows that pattern of a percent, which is the part over the whole times 100. So percent yield is the actual yield divided by the theoretical yield. I call him Theo, times 100. So if you didn't drop any pizzas on the floor, if you didn't burn any, then your theoretical yield and your actual yield would be the same, and you'd have a 100% efficiency, a 100% yield, and that would be awesome. But if you drop one on the floor, you made 2 out of a possible 3, and so you've got a 66.67% efficiency. Any questions? This is kind of summarizing. The limiting reactant is the one that limits the reaction, and it is completely consumed. The reactant in excess is any reactant that is not completely used up, and there could be many of them. There's only one limiting reactant, and the rest would be in excess. Theoretical yield is the amount made based on the amount of limiting reactant. The actual yield is how much was actually used, and there again is the percent yield equation. So let's apply this to a chemical reaction. We were looking at this reaction earlier, methane plus oxygen, forming carbon dioxide and water. And we look at this picture representation, and we see one of these and 2 of those, and you can imagine pulling these little models apart and putting them back together in a different way. And we see that for every 1 molecule of this, it reacts with 2 molecules of oxygen. Well, what if we have 5 molecules of methane and 8 molecules of oxygen? What's going to happen? We apply the same process that we did with the pizza. We take the quantity of each reactant and figure out how much product we could make. So if we have 5 molecules of methane, we're going to get 1 molecule of carbon dioxide for every molecule of methane, and so we should end up with 5 molecules of CO2. And then we look at the other reactant, 8 molecules of oxygen, and we get 1 CO2 for every 2 molecules of oxygen, so that would get us 4. And then we look, which is the smaller number, 4 or 5? Well, 4 is smaller. So that tells us that the oxygen is what limits the production of the product. And so 4 carbon dioxide molecules is the theoretical yield. Well, we can do this with masses of chemicals as well as numbers of molecules. And there are different approaches to solving these problems. The way your book approaches it is they say, well, you're given a mass of A and a mass of B. Convert to moles and then to moles of product and stop there and ask yourself which is smaller. Okay? And if this method makes sense to you, by all means, go ahead and use it. I find that it tends to be a little confusing to students. There's another way that's maybe slightly longer, but is conceptually more simple, and so that's what I do. So then they say to take that smaller number of moles of product and find the mass of the product. But I'll show you the way I do it. So here we have ammonia can be synthesized by this reaction. What's the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen? So here we have a balanced chemical equation, and we're given amounts. Use the equation to organize the information. So I have a mass of hydrogen, so I'm going to write that. Yeah. I'm going to write that under here. Yes, we hear you, Mr. Engineer. Wow, that's just nice. Okay, so this is the mass of that reactant. This is the mass of this reactant. What's different about this problem from the ones we did last week? How many masses do I have here? I've got 2 masses. Last week they only gave us 1. So here they're giving us 2. When they give you masses of 2 reactants, it's almost certainly a theoretical yield problem, a limiting reactant problem. What are we trying to find here? Theoretical yield of ammonia in kilograms. That is the mass of ammonia in kilograms. So question mark kilograms. So what I prefer to do is just do 2 stoichiometry calculations. So I'm going to go mass of hydrogen to moles of hydrogen to moles of ammonia to mass of ammonia. And then on the second line, I'm going to do mass of nitrogen to moles of nitrogen to moles of ammonia to mass of ammonia. And then I'm going to see which one is smaller. So let's see how that'll look. So we've got the grams to moles to grams. So I'm going to put the kilo in a different color there, because we're going to ignore the kilo for now. We're just going to pretend he's not there. I put him in a different color so we can see him, but we're not going to worry about canceling him out or anything just yet. This happened in a problem last week too, and as we saw, it took care of itself. So we need to go to moles of hydrogen, and then we need to go to moles of ammonia. And then we want to go to grams of ammonia. So I've got moles down here, and hopefully you're getting comfortable with this. It's not nitrogen, it's hydrogen. And grams of hydrogen. Turn it. There we go. Okay, so grams cancels, but that K is still sitting there. Well, what's the mass of 1 mole of hydrogen? Well, the mass of 1 mole of hydrogen atoms is 1.008, but this is H2. So it's going to be 2.016. And what's the ratio of ammonia to hydrogen? 2 to 3. We get 2 moles of ammonia for every 3 moles of hydrogen. So 2 to 3. And then over here we have to calculate the molar mass of nitrogen. I lost the last digit in my head. 3 times 1.008 plus 14.01, 17.034. Didn't leave quite enough room. Okay, so let's do the math there. 5.22 divided by 2.016 times 2 divided by 3 times 17.034 equals. How many significant figures should my answer have? 3. Because I started with 3. So we'll get 29.4. And what is the unit? It's kilograms. This K did not get canceled out. The grams did, but the K didn't. And then over here I have grams. So there's kilograms of ammonia. Now, if that's confusing, go right ahead and do the conversions. Some of you can convert from kilograms to grams kind of in your head just by moving the decimal point. As long as you're doing it correctly, that's fine. Or you could stick a term in here to convert kilograms to grams, but then you'd need to stick another term in here and convert back, and you'd find that those would actually cancel themselves out. So, are we done? Is this our answer? No, because we don't know how much ammonia we could make from this mass of nitrogen. So we're going to do a very similar calculation. And once you learn this pattern, doing the calculation is just not that bad. Okay, so here we're going to start with 31.5 kilograms of nitrogen. And I'm going to convert to moles of nitrogen. And there's grams of nitrogen. And then I'm going to convert to moles of ammonia. From moles of nitrogen. And then grams of ammonia, moles of ammonia. So all the units cancel out. I didn't make him blue this time, but that K is not canceling out, and so it's going to end up over here. We're going to end up with units of kilograms of ammonia. Well, what's the molar mass of nitrogen? N2. It would be 28.02. And the ratio here, there's 2 moles of ammonia for every 1 mole of nitrogen. So 2 to 1. And look at this guy. That's exactly the same. All we have to do is copy down the number. We don't have to figure it out again. So 31.5 divided by 28.02 times 2 times 17.034. And I'm getting 38.3. Did I do that right? Yeah. So 38.3 kilograms. We've got 2 answers. Don't add them together. I sometimes see students do that. It's creative, but you know, most of chemistry, creativity is not encouraged. We have areas where you can be creative, but this isn't one of them. We want to choose the smaller one. Don't make it harder than it needs to be. You find the mass of product for each reactant, and then you just choose the smaller number. that is the answer. That is the theoretical yield. On mastering chemistry, on an exam, if this were a multiple choice, then you would have to enter it or select a choice. On a lab or a worksheet, if there was a question like this or a written portion of the exam, you have to indicate which of these answers you're choosing. If you leave off the box, if you do it like that, I might give you partial credit, but you won't get full credit because you didn't choose an answer. So put a box around the smaller one. That's your limiting reactant. If you want to write a nice sentence at the bottom, the limiting reactant, the theoretical yield is 29.4 kilograms, that's awesome, but not absolutely necessary. So what's the limiting reactant here? The hydrogen. So if it asks you what's the limiting reactant, you'd need to indicate that somehow. But that's our limiting reactant. Sometimes we call him LR. The hydrogen is limiting the reactant. Limiting the amount of product. Any questions? Yes?
What if there's two products?
What if there's two products? That's a good question. Usually it will ask you about a specific one. So what's the theoretical yield of ammonia? It will specify which one you're interested in. If it doesn't, if it just asks you perhaps what's the limiting reactant and doesn't even ask you how much product or what the theoretical yield is, then just choose one of the products and do the calculation for that. Find the smaller one and then go back to where it started from, and that's your limiting reactant. It's a good question. Any other questions? Let's do another one. Mining companies use this reaction to obtain iron from iron ore. The reaction of 167 grams of iron 3 oxide with 85.8 grams of carbon monoxide produces 72.3 grams of iron. Determine the limiting reactant, the theoretical yield, and the percent yield. Again, use the chemical equation to organize your data. So it tells us that we have 167 grams of Fe2O3, 85.8 grams of carbon monoxide, and that it produces 72.3 grams of iron. Now this is one that does have two products. Determine the limiting reactant, the theoretical yield, and the percent yield. What is this mass here that they gave us? Is that one of those things we're supposed to find? No. What would we call that? It's the actual yield. So this is the actual yield. So you have to take these words and figure out exactly what they're meaning. That's the actual yield. So this is like the 2 pizzas. And that's something, if you don't know what the percent yield is, they have to tell you that. You can't just guess at that. So what we need to find is we need to find the theoretical yield, the mass of iron that could be produced from these 2 amounts of reactants. So we need to find grams of iron, and that's going to be our theoretical yield. The theoretical yield is always calculated using stoichiometry. Sometimes it's tempting to look at these and say, well, there's a lot more of this one. This is probably the limiting reactant. That can be very deceiving because it depends on the relative masses of these. It also depends on the coefficients. So you really, it's just complete chance whether you get that one right or not. I wouldn't recommend it. 167 grams of Fe2O3. Grams to moles to moles to grams. And the stoichiometry thing is really important. So If it's not making sense to you, please ask me for help during lab. I don't want to bore the class, but I also don't want to leave people behind in the dust. So then moles of the other thing. This time, because they gave us an actual yield of iron, we're looking for the iron. We don't care about the carbon dioxide in this case. Moles of iron oxide. And then grams of iron. So the molar mass of iron is easy. It's just on the periodic table, 55.85. And let's just take care of our units here. The mole-to-mole ratio is always easy because it's just from the balanced chemical equation. This time it's 2 moles of iron for every 1 mole of the oxide. So 2 to 1. And then we need to calculate the molar mass of the iron oxide. So that's 2 times 55.85 plus 3 times 16, 159.7. Again, I'm using molar masses that are rounded to 4 significant figures. You do want to make sure that that's not going to be the limiting number of sig figs. Here it's going to be 3. So rounding those to 4 is fine. Don't round them any further though. So 167 divided by 159.7 times 2 times 55.85. I'm going to write down more digits this time because this is not a final answer, is it? We may need to use this number in another calculation. So it would really only have 3 sig figs, but I'm just going to put a couple extras down. So 116. Anybody else get that? Thank you. Now we're going to do similar calculation, but starting with the carbon monoxide. So 85.8 grams of carbon monoxide. Again, we're following that pattern, grams to moles to grams. Grams of CO to moles of CO. Then we're going to moles of what we're interested in. Sometimes students decide to do the other product here. That's not going to help you. You might do a lovely calculation, but it's not going to get you where you need to be. We're going to the same product. So moles of iron to grams of iron. And then always get those units in place and make sure that they really do cancel out. We don't want any wishful canceling. So now some of this is easy to fill in, like the last one. The molar mass of iron has not changed in the last 5 minutes. The moles of iron is still the same, 2 moles of iron. And then we've got 3 moles of carbon dioxide this time. And we need the molar mass. Nope, that's wrong. That's CO2. Should be able to do that in my head, but my head's not working very well. 28.01. So 85.8 divided by 28.01 times 2 divided by 3 times 55.85 equals 114.053 grams of iron. We got 2 answers. Now what do? We pick the smaller one. So this one's smaller. So determine the limiting reactant. What is the limiting reactant? Well, you've got your smaller amount of product. Look back and see which reactant gave that to you. Which one gave you the smaller amount? That's your limiting reactant. So the limiting reactant is carbon monoxide. That's answer number 1. What's the theoretical yield? It's the smaller amount, right? So now expressing the theoretical yield, we could round that to the correct number of significant figures, 114 grams of iron. What's the percent yield? Well, we need to do a calculation for that. And as often happens, I've run out of space, so we'll go up here. The percent yield is the actual yield, which they gave us, 72.3, divided by the theoretical yield. I'm not going to round it here because I don't want to introduce rounding errors. Times 100. What happens to the units there? They cancel out. Grams over grams cancels out. That generally happens in a percentage. If it doesn't, you're not doing it right. So 72.3 divided by 114.053 times 100. And that is a final answer, so I'll round it, and that should be 63.4%. And that is the percent yield. So I've got 3 answers for this one. Any questions? Yes?
On the test, you'll walk us for that box, won't you? For the grams, that means it's not grams, it's figures.
Well, question is, would you get docked because this isn't rounded to the correct number of significant figures? Possibly, but right down here, I did round it. So here I said the theoretical yield is 114 grams and rounded it. So I would look at that. It's a good question. Any other questions? Yes?
What if we do like you did and like underline a significant figure? Would that count, or do you want us to actually write down around?
That's a good question. If you underline the last significant figure, does that count for showing correct sig figs in your final answer? No. I want the final answer actually rounded. Okay. It is better, though, to carry extra digits, and I would prefer someone to give me too many digits rather than not enough digits. But in your final answer, you should round it. On a multiple choice portion of the test, I will not try to trick you by putting, I wouldn't put this answer and this answer for the theoretical yield and try to nail you on sig figs there. But we need to practice always doing significant figures correctly. Any other questions?